Okay, hello everybody. In today's video, we are gonna see the solution to this problem named Vasya and Tree. I leave the link to this problem in the description, also the link for the code stored in a public repository. Okay, so let's hop right into the solution of this problem. Well, the description of this problem. It actually says that given a tree named G rooted at vertex 1 for vi, di, and xi, which are going to be at most 3 to the power of 5. I mean, 3 times 10 to the power of 5 triples of these three numbers. We're going to add xi to the value of all those nodes that have height at most di respect to vertex vi. Okay? All the node values are initially 0, so we're going to be adding and adding, just adding. So the least value that one node can have is 0. Okay? And we have to print the final value for every node. Okay, and the upper bound for vi is going to be at most n. The upper bound for di is 10 to the power of 9, as well as for xi. Okay, so this is the problem description, but before solving this problem we have to see an example for us to see what they mean. Okay, so here we have three triples. Okay, so they are telling us. Excuse me, I'm gonna set the server pointer. Okay, they are telling us for all those nodes that are at height at most one, respect to vertex one, we are going to add a value of 1. So initially all these have value 0. So since they are asking us for height at most 1, we are gonna add 1 to 1, 2, and 3 because those are at height 1 respect to vertex 1. Remember that the tree is rooted in vertex 1. Okay, so 1, 2, and 3 now have a value of 1. Okay, so let's process the second query, in which all those nodes with height at most 0 respect to vertex 2, we're gonna add a value of 10. So only for vertex 2 is this value of 10. So now it has a total value of 11, one that we had added previously, and the 10 that we added now. Okay. Now all those vertices with height at most 10 respect to 4, we're gonna add a value of 100. So there are no other vertices here below vertex 4, so we add 100 to 4, only to 4. So we have final values of 1 in vertex 1, 11 in vertex 2, 1 in vertex 2, 3, 100 in vertex 4, and 5 that we never had a query about vertex 5, so it's left with 0. Well, now that we understand the problem, let's not see the solution. We first have to know this other problem that is gonna help us understand how we are gonna do this problem. Okay, once we understand this other problem, the solution to Vasya and Tree becomes quite clear. Okay, so this is interval covering. I don't know the exact name for this problem, but let's leave it as interval covering. Okay, if the problem says that given some intervals, at most 10 to the power of 5 intervals, for every index, we're going to print the number of intervals that cover this index. The intervals are going to be from 0 to 10 to the power of 5, the limits of the interval, of every interval, okay? And well, a name approach of this problem would be for every interval run a loop from Li to Ri and add 1 to all indices it touches. It's gonna give us time limit exceeded because we are gonna have at most 10 to the power of 5 intervals, and just by fun I can give you the intervals 0 to 10 to the power of 5, 10 to the power of 5 times, and you have a total complexity of 10 to the power of 10. That's all. So that's not feasible. So the solution for this problem is for every Li add 1 in index Li, and for every Ri subtract 1 in the index R r plus 1. And then we run a loop from 0 to n and add the content of every index to a sum variable. The answer for every node will be the current value of sum. How do we do that? Well, if you didn't understand literally this solution, we're gonna see the example. So here we have indexes from 0 to 7. Here we have the intervals that they are giving us as inputs. Okay? So we have the interval 2, 4. So what are we going to do? We are going to add 1 in position 2 and minus 1 in position 4 plus 1, which is equal to 5. And the same for these other intervals. So our array would look like 0, 0, because we didn't touch 0 and 1 with these intervals. But now that we touch the interval 2, but now that we are at index 2, we have two intervals that touch vertex 2, so we add 2. We have one interval that starts with 3, so we add 1 in 3. We have one interval that starts with 4, and here in 5 we have minus 1 because we have one interval that ends with 4. So to the position 5 we had to add minus 1. And for index 6 we have minus 2 because we have two intervals that end with 5. So we add minus 1 for both of them, so we get minus 2 in vertex 6, and we add minus 1 to vertex 7 because we have this one that ends with 6. Okay, so the array of answers for this problem would be 0, 0, 2, 3, 4, 3, 1, 0. As I told you in the solution, we just have to add every value from this second row of this table. We have to add it to a variable sum. We don't actually need a second array to start the answers. Okay, so we just have a variable sum and we're gonna have 0, 0, then we add 2 here, we add 1 here and we get 3, we add 1 here and we get 4, we subtract 1 here and we get 3, we subtract 2 here and we get 1, and we subtract 1 here and we get 0. And you can actually prove the correctness of this algorithm. Okay, that's the interval coverage problem, the easy version for it. There's another more complicated version of this problem that we're gonna examine in another video. Okay, we can actually do these problems with values for this interval. So let's say that this interval that covers from 2 to 4 adds a value of 7 for every of those indexes that it touches. So it doesn't matter. Instead of adding 1, we add 7 to the position 2 and we subtract 7 to the position 4 plus 1. So here we have in the position 2 we have intervals that add values 7 and 8. So here in index 2 we would have 7 plus 8 which is equal to 15. And of course in node 5 we would have minus 15. Okay, but then we add 9 and 8 and that changes, that alters the value. Okay, so that's everything we have to do for this problem. Now let's hop in the solution of Vasya and Tree. Okay, so first of all, let's transform this problem in something that we already know. For example, we have this. If we were given a linear tree, which is this sequence of nodes that are like consecutive, that are forming a line, we have no ramifications. It would be pretty easy to notice that we have an interval covering problem. Why? If they give us the queries that all those nodes that are height 3 from 1 at 1, so those nodes are gonna be like heights 1 to 4, okay? Because we're gonna be covering This is height 0, this is height 1, this is height 2, height 3, and height 4. So actually, when they give us this VI, this first node, instead of taking these nodes, we're gonna take the height of this node, and that would be the left point, the left limit of the interval, and the height of this node plus the height that they are giving us is gonna be the right limit of the interval. That's how we transform this problem in the interval problem that we were just looking at previously. Okay, but that doesn't help us a lot because we're gonna have graphs that are gonna have ramifications. Okay, but remember that every path from root to leaf is a linear graph. So basically, we just have to generate all those paths from root to leaf and apply the solution to this other problem. But of course, we have to do it optimally. And that's it. That's everything we have to do. How do we achieve uh, these all these paths from root to leaf? Then well, that is just an in order that's just an in order traversal of a tree. So let us just do an in order traversal, and we are gonna add the list of queries that are related to this node, and we're gonna add them to our segment array. To this array, we're gonna add those queries, and let us process them. When we don't need this vertex anymore, of course we're gonna go up in the tree, and then we're gonna see the other ramifications. So whenever I go up in my DFS, I have to undo all the changes that I did in this node. We're gonna see this in code so that you understand it better. Okay, we don't care too much about main function because it's just reading the graph and reading the queries that they are giving us. Basically, there are m queries, and we're gonna store them for every node. But basically, what we are doing here is that we have a map of an integer key and a long value, and we're gonna store this map for every node. So if they give us the same height like twice or thrice or as many times as they want, then we're just gonna add this to our current value at that height. Okay, so that's basically what we are storing here, a map of integer. I mean a map of integer and long. Okay, and even though these all are long, well, but that's another thing. Okay, so we start our DFS with 1 because we are doing an in-order traversal from 1. So basically, our in-order traversal is just this one. We assign parent of B equal U, and we start DFS from B, and we make sure that we don't see the same vertex twice. That's it. Now, what we're doing here is that we are declaring this array named segment, actually set, in which we are storing the information about intervals. This is our array of intervals, okay? And this variable sum is gonna be helping us to get the answer for every node, and we're gonna store it in our ends array because we don't traverse the tree with the vertices in order. Okay, so basically what we do is that we run over its list, and what we did previously in the current height, you see that the variable height is going to be increasing and decreasing whether we go farther, or lower or upper in our tree. When we go lower, we increase our height. So we're gonna increase our the value for our current height in x point second, which is the same that we read here, this third variable, which is xi. Okay, and we just have to be careful about the right upper bound of this interval. It's gonna be h plus x point first, but we gotta make sure that it fits in an integral. Well, actually, that it fits in our array, and we don't want to make this array too long. You remember that the every di is gonna be at most 10 to the power of 9, so we don't want to overflow its capacity. So we just ask if it is less than or equal to n, and we are gonna decrease x point second in 1/8 beyond than what we have computed. Okay, now we add the value of seg in position h, which is the current height, to our variable sum, and we store that sum in our answer array. We increase height, and we undo all the things that we have previously done. We decrease height, we subtract the the value on our current height to our variable sum, and we run over its list again. So that's everything that we had to know. This is actually the code that gets accepted. I hope you enjoyed this video, you guys. I hope this video was useful for you, and see you in another video. Bye bye.